Good evening, esteemed judges. We're Team USC, and we're so excited to share with you the culmination of our month-long SCUDEM 2025 differential model.
For our question, we selected problem B, an AI Ouroboros. In this question, we want to analyze how over the course of multiple generations, when being fed synthetic data, we want to see how an AI slowly degrades over time, leading to eventual model collapse. The key questions we want to answer are how does this impact the model over many, many generations in the future and how it can have implications on the accuracy of its responses. We also want to see how using multiple different types of inputs affects this, what is known as model poisoning. And we also want to see how a mix between using synthetic data and a mix of human-made data or authentic data can help combat the response and maybe diminish how much the AI degrades. We basically reference a lot of our information from a research paper written in 2024 called AI Models Collapse When Trained on Recursively Generated Data. In this research paper, it takes a model and then it basically re-inputs the outputs from previous generations. And we can see that while some responses are more commonly generated than others, those rare responses, when re-inputted multiple and multiple times, they tend to be filtered out. So those rare responses eventually completely diminish, and all that is left are the common responses, and it eventually leads to model collapse. The research paper itself uses this method multiple times using multiple different generations, and then analyzes those.
So as we've already described, in the research paper, multiple models are used with the same model collapse method, recursively generating data, to understand model collapse. We modeled this on a simple Gaussian model, and we'll prove shortly that it approximates the different types of models like LLMs and VAEs that are trained in the paper. So one advantage of our simple Gaussian set is that it's best for efficient building and testing of our model. The mathematical basis that we're talking about is because statistical approximation error, which is basically, as you saw, the tails removing themselves and probable events becoming more probable. This is true for higher dimensional data like you would use in an LLM as well. For that case, standard deviation would be equivalent to the negative log perplexity when we're graphing that, and others for their respective models. A universal trend that we've seen is information loss. This is basically the statistical approximation error, where the less common events will eventually be removed entirely from the set. And this can happen when the model is trained on too much synthetic data or it has a finite sample size. The explicit relation, this is to prove the relation between our model being an approximate for the higher dimensional data. And this is because any sample variance in our model, which will be sigma squared, let's say n+1, is drawn from the previous model's distribution, normal distribution for sigma n. So now let's take our variance. We know that since it is a continuous random variable, it has its own variance. We can calculate this using the formula for variance of continuous random variables. And then we can use the expected value to calculate the difference between generations and approximate the variance loss. We find that it's directly proportional to the estimation error, right? You can see right here, for this generation, it's approximate to this. The loss is nonlinear, which means that it does work for a higher dimensional nonlinear set. We can see this through the last point. If we look at the general measure of diversity, which would be our metric, we see that it is, again, nonlinear for some f. It's nonlinear. The basic assumptions that we have for this model is that complete synthetic training, like we've done, provides a good theoretical basis to understand model collapse, and we can extrapolate from there to answer our other key questions involving human data as well. The second assumption is that information loss leading to model collapse is inescapable. We modeled using this as a constant because we know that information loss will always be present mathematically. The initial normal model distribution and values that we did, we use these because it approximates real-world data. That was our assumption with high probability. And the final thing is that our initial constraints were that authentic generator was generated via sigma n, sigma squared n for initial value 1.0 and 1.0. The models were all created in Python and our plots were made with PyPlot.
Now let's speak a little bit about how we derive an explicit ODE for our model. So if we take the sample variance estimator of the n+1 sample variance estimator for m samples of generation, we see that in the top left that is equal to m-1 over m times the variance of the nth generation. So from that, I can expect that the n+1 variance is equal to the m-1 over m times the nth variance. And then we can rearrange this equation algebraically to get a discrete recurrence difference between the n+1 variance and the nth variance. And that proves to actually be linearly proportional, linearly related to the current nth variance. But each generation draws from an approximation, as we've already described, that has already lost variance because we're training it on synthetic data. So that means it can't actually be linear. So instead, we let it be quadratic and we let the discrete difference between the generations be our derivative, and that's how we derive our ODE with our variance as a function of generations. And this ODE actually proved to be quite simple mathematically. So we were able to find an analytical solution in separating the variables and integrating, which resulted in the expression that we see in the bottom right. Although we did, after we solved it, take the expression we took the square root of it and added the C term so that the limit didn't always approach zero in case we have more human data rather than synthetic preventing collapse. Now let's speak a little bit about our parameters and the stability of our ODE. The A and K terms of our solution and ODE are decay rates, which just tell us how fast collapse happens. The B is an offset, which shifts it along the axis because it's being added to the N in the analytical solution. And we have our C, which is our fitted standard deviation floor. Like I said, the limit of the A over root N plus B term approaches zero. So if we have less synthetic data in order of human data, we know that the standard deviations will not converge to zero, and instead they'll converge more or less to C. So we added that term to our analytical solution. And the exact values we got are generated from our SciPy Python script. Now let's speak a little bit about our experimental results. On the left, we see a graph using only synthetic data, which you can see provided a very extreme example of model collapse, meaning at a very high K value in the ODE. In the top right, we see that we had not very much model collapse because in that example, we use no synthetic data. So you can see that there was not much model collapse, and in fact, the standard deviation stayed around the initial value of 1. And in the bottom right, you saw a limited amount of model collapse because we use only half synthetic, half human data. So we see the standard deviations drop a little bit from the initial 1 value, but not very much.
Let's just go over some limitations and strengths of our model. Due to the constrained random generation method of our Gaussian model, the data points between samples always vary very slightly. But to combat this, we basically run each generation many times and then we average out the numbers, and that creates a very comprehensive model that we can use. And then, however, our model, since it is much simpler than a large language model, we measure it using standard deviation. However, a large language model is measured with log perplexity. However, using a Gaussian model tends to have it be less computationally expensive, meaning that these experiments can be replicated very, very easily. It also lets them be reflected onto many different questions we can answer and helps model the data better.
So let's just link this back to our initial key questions. We wanted to answer how model degradation can be measured over time by being fed synthetic data. And what we found here is that over time, when being fed synthetic data, models are mathematically guaranteed to collapse on wholly synthetic sets, and also in terms of model interaction, sufficient amounts of synthetic data training can lead to model collapse. We've also seen, though, that this is not necessarily absolute. Human data injections can significantly alleviate the impact. We've seen from before, adding in human data, even in very minute proportions, can grossly increase the floor that the model collapse would reach. And this is a proven strategy for releasing model collapse over time. We should also discuss what we've actually managed to achieve in this project. We've managed to do all of this model collapse analysis based on Python scripts using our differential equation that we found. We based this off the research paper that we discovered linked to the initial data for AI Ouroboros. We looked through their supplementary materials to get the raw data in order to match our differential model and ensure it's accurate. We were able to perform stability analysis and parameter analysis on this afterwards. And finally, we were able to assess the model's strengths, weaknesses, and connect it back to our initial question. Thank you so much for coming on this journey with us as judges. We hope that you learned and enjoyed just as much as we did during this month-long process. It was truly transformative. Thank you so much, and Team USC signing off.